Dr. J. Maheshwari Vasiran. Here I am going to explain the concept of mutarotation. First, muta means change. So it literally means a change in rotation. The specific rotation of a molecule never changes, but the specific rotation of an entire solution can change. This is because the molecule can change between isomers in some cases, such as glucose. Okay, here I am going to explain the concept of mutarotation with an example. Here I am taking glucose as the example. Okay. Let's look at what happens when we put pure alpha D glucose into water and measure the specific rotation over time. Okay. At first, it starts out at 112 degree, just as we would expect, but it slowly starts to change until it reaches 52.5. Now let's look at what happens when we put pure beta D glucose into water, and measure the specific rotation over time. Once again, it starts out where we would expect it at 18.7 degree, but it slowly changes until it reaches 52.5 degree. Here, I want to explain chiral molecules, chirality, optical activity, specific rotation, and the symbol of specific rotation. Okay. Chiral molecules are nothing but the molecule which possesses chiral carbon or carbons in its structure. Chiral carbon is nothing but a carbon which is surrounded by 4 different groups in its structure. When a molecule possesses chiral carbon or carbons in its structure, it can exhibit the property of optical activity. Optical activity is nothing but when a plane polarized light is passed through the solution of a chiral molecule. It can rotate the plane polarized light towards right, that is clockwise direction, or left, that is anti-clockwise direction. Every molecule has a specific rotation. It never changes. But in the solution state, it can change. That is due to anomeric forms of cyclic structure of a chiral molecule. Okay. In chemistry, specific rotation is a property of a chiral compound. It is defined as the change in orientation of monochromatic plane polarized light per unit distance concentration product as the light passes through a sample of a compound solution. Okay, usually the specific rotation is denoted by the symbol of alpha. This is if the wavelength of the light used is 589 nanometer, the sodium D line, the symbol D is used. If the temperature is omitted, it is assumed to be at standard room temperature between 20 to 25 degrees Celsius. Optical rotation is either plus or minus. Plus means the molecule rotates the plane polarized light towards the clockwise direction. That is dextrorotation. The molecule is dextrorotatory. Minus means when the molecule rotates, the chiral molecule rotates the plane polarized light towards left or anti-clockwise direction. Therefore, the molecule is levorotatory molecule. Look at this structure. This is the open chain structure of D-glucose molecule. Okay. Glucose contains 6 carbon atoms in its structure. This is the structure proposed by Fischer. This is the two-dimensional representation of the glucose molecule. Here, the first carbon possesses the functional group of aldehyde here. The second, third, fourth and fifth. These 4 carbons are chiral carbons of glucose molecule. And here the symbol D is given for the glucose molecule is based upon the distant hydroxyl group. Look at the structure, the distant hydroxyl group. This is the distant hydroxyl group. Distant hydroxyl group means the hydroxyl group possessed by the distant carbon atom. Here, fifth carbon is the distant carbon atom of the functional carbon. And this sixth carbon is the terminal carbon atom. The hydroxyl group, if the hydroxyl group of the distant carbon atom located at the right side of the molecule, then it is called as D. If it is located at the left side of the molecule, then it is denoted as L. This type of notation is specific for carbohydrates. Okay, this type of nomenclature used for carbohydrate. And look at these structures. These are the structures given for the glucose molecule by the Haworth. Haworth shows the molecule. Okay, these cyclic forms can be in equilibrium with open chain form. That is, each form can be converted into one form into another. It is with okay. This is the Haworth structure of D-glucose. Haworth giving these cyclic structures, for the glucose molecule. Okay, and there are two forms. The forms are alpha and beta forms for the glucose. This anomeric forms shows the change in composition of hydroxyl group at C1 carbon. And center one is open chain. This is beta form and this is alpha form. Here alpha form is the highest energy state because it is in the steric repulsion of the neighboring hydroxyl group. But here in the beta form, it avoids the steric repulsion exhibited by the nearby hydroxyl group. And this is the Newman projection. This is the Newman projection formula for the glucose molecule. The initial rotations of plus 112 forms of glucose. The initial rotation of plus 112 degree or plus 18.7 degree. Okay, here in the book it is given as 113 and 19. Accurately it is 112 degree and 18.7 degree are caused by the presence of alpha D-glucose. Alpha D-glucose with a specific rotation of plus 112 degree or beta D-glucose with a specific rotation of plus 18.7 degree respectively. Okay, in the solid state, these two forms of glucose are stable. You should remember in the solid state, these two forms of glucose are stable. However, when either form is placed in solution, it slowly forms the other anomeric form via the open chain aldehyd form. And the gradual change in specific rotation is attributed to the establishment of equilibrium between the two forms. The final value of 52.5 degree plus 52.5 degree. This is the equilibrium state of the solution, which exhibits the specific rotation of 52.5 degree. The final value of 52.5 degree corresponds to the equilibrium mixture of the alpha and beta forms. Actually, this value is not an average of plus 18.7 degree and 112 degree. Okay, this value is not an average. Therefore, this implies that the equilibrium mixture does not contain equal amounts of the two anomers. Calculations have shown that it contains 64% of beta form and 36% of the alpha, along with less than 1% of the unisolable open chain aldehyde form also exist. Okay, Look at this graph. Here in y-axis, the specific rotation is given. In the x-axis, it is recorded along with the time. Initially, suppose we are taking the alpha form. In the initial stage, the optical rotation of the solution, alpha D glucose solution, is 112 degree plus 112 degree. This gradually decreases with the time and reaches the equilibrium value of 52.5 degree. Suppose we are taking the beta form. Suppose we are taking the solution of beta form, the specific rotation gradually rises from the 18.7 degree towards the 52.5 degree. 52.5 degree is the equilibrium value. Okay. How it happens? Mechanism of mutarotation is not completely understood. However, the generally accepted mechanism involves a simultaneous attack by an acid and a base to yield the open chain aldehyde form, which then rearranges to give the other cyclic form. Okay, look at this diagram. This is beta D-glucose in the open chain structure, and this is alpha D-glucose in the presence of an acid or base, acid and base. Okay, it abstracts a proton. The oxygen atom in the pyranose ring abstract the proton from the solution, and this bond cleaves to form the open chain structure. Further, it again abstracts a proton from the solvent to form another cyclic form, that is alpha D glucose. These three forms are interconvertible. This type of cleavage either follow exocyclic or a endocyclic mechanism. Okay, my dear students, in this class we have discussed about the concept of mutarotation. Mutarotation is the property of a chiral molecule, especially cyclic chiral molecule. Not all chiral molecule exhibits the property of mutarotation. Certain cyclic chiral molecules can only exhibit the property of mutarotation. Here I have explained the concept with the example of glucose. Glucose usually in three forms, that is cyclic, acyclic. In the cyclic form, it exhibits alpha and beta anomeric forms. Okay, the specific rotation of alpha form is plus 112 degree and the beta form is 18.7 degree. Suppose in the solution state of beta form, the specific rotation gradually increases and attaining the equilibrium value of 52.5 degree. Suppose we are taking the solution of the alpha form with a specific rotation 112. In the solution state, the specific rotation gradually decreases and reaches the equilibrium value of 52.5. One cyclic means one cyclic form to the other form. Here the alpha and beta form are called as anomeric form. Anomeric forms are the change in the configuration of hydroxyl group at the C1 carbon only. Okay, that's all about the concept of mutarotation. Thank you, my dear students.